Today we're going to cover section 11.1, sequences and summation notation. So a sequence, let's write a definition here, is a pattern of numbers. Okay. So A sub n is how we read this notation. It's an A with a little n right next to it. And we read it A sub n. That n is representing which term in the sequence. So let's say I had A sub 1. That's the first term in the sequence. Okay, if I have A sub 7, that's the seventh term in the sequence. Okay, so when you see A sub n, that means the nth term in the sequence. Okay, so an infinite sequence is a function whose domain is the set of all positive integers. That means your n can only be positive whole numbers, which makes sense because if we're talking about the first term, the second term, the third term, we're not talking about in-between terms. You can't have the 2.7th term in a sequence. That doesn't make sense. Sequences whose domains consist of only the first n positive integers are called finite. That just means, this word finite, means there's an ending term. Okay, so that means the sequence starts at one number, ends at another number, and that's it. Whereas infinite means it goes on forever. Okay, so some sequences that you guys might see are all of the odd numbers, right? So let's say we've got 1, 3, 5, 7. So that's a sequence that never ends. So this would be considered infinite. If I asked you guys for the first 10 odd numbers, that would be finite because it would end after the 10th term, okay? But we'll get to that. All right, so finding terms in a sequence. If I want to find the first 4 terms of each sequence, that means I want A1, A2, A3, and A4. So what I do with the 1, the 2, the 3, and the 4 is I plug them in for n. So if my sequence says 3n plus 4, I'm going to do 3 times 1 plus 4. That gives me 7. Here I'll have 3 times 2 plus 4, which is 10. 3 times 3 plus 4, and 3 times 4 plus 4, which tells us that the first 4 terms of our sequence are 7, 10, 13, 16, and then, oops, it could continue on forever. Okay, and you notice there's a pattern here. We're going up by 3 each time. In the next lesson on Monday next week, we'll be talking about how to come up with an equation for this system, or for this sequence. All right, so let's go ahead and do the next one. So we're going to plug 1 in anywhere you see an n. So we've got -1 to the first power over 3 to the first minus 1. Okay, now I want to simplify that. So that gives me -1 on top. 3 minus 1 is 2. And so that can't be simplified any further, so that would be our first term. For the next term, plug 2 in for n. Notice that gives me a +1 up top. 9 minus 1 is 8. Okay, and then we can keep going. negative 1 on top, 27 minus 1 is 26. And finally, negative 1 to the 4th, 3 to the 4th minus 1. So we have a positive 1 on top because we're raising to an even power. On the bottom, 3 to the 4th minus 1 gives me 80. Okay. All right. So the first 4 terms of our sequence are negative 1/2, 1/8, negative 1 over 26, 1 over 80. Okay. All right, so what does the graph of a sequence look like? Let's say I have the sequence over here. You normally wouldn't have to have these brackets, but sometimes you see them. So let's say I want the first 4 terms. What goes on the x-axis is your term number. So if I've got my first term, second term, third term, and fourth term, let's find the first 4 terms again. A1, A2, A3, and A4. So if I plug a 1 in for n, I get 1. Plug a 2 in for n, plug a 3 in, and plug a 4 in. Okay, so the terms in my sequence are 1, 1/2, 1/3, and 1/4. Okay, now what goes on the y-axis is the actual term value. So we need to, the biggest number I have here is 1, so I'm just going to go up to 1, and that's my first term. When n was 2, I got a value of 1/2, so that's halfway up. Okay, if you want to mark that, you can. When I was at 3, I was 1/3 of the way. And when I was at 4, I was 1/4 of the way. Okay, now it's important to not connect the points. Okay, because again, the only numbers that we plugged into this sequence were the whole numbers. So I don't want to have a line going through because that doesn't mean anything. So I only have my first term, my second term, my third term, my fourth term. Now I could keep going with the points, but I can't connect them with the line. Okay. All right. So there are a couple different, actually, I should go back for a sec. These 2 types of equations, and actually this one as well, these are called explicit formula. So an explicit formula, or definition, sometimes you see that word, means that you're given an, well, not really an equation, well, kind of an equation, but so we're given a formula, plug values in for n to find individual terms. So the way this formula worked here was that if I was looking for the first term, I would plug 1 in. If I was looking for the third term, I plug 3 in. If I find the 10th term, I plug 10 in. Okay, so that's called an explicit formula. Now, a recursive formula is another type of way to describe a sequence. And it says, define the nth term of a sequence as a function of the previous term. The formula must always include the first term, which is a sub 1, and an equation that describes the nth term, a sub n equals, okay, in terms of the previous term. So if you look at a sub n minus 1, once we put some numbers in here, you'll see that that is referring to the previous term. Okay, now using this first recursive formula, I know that my first term is 5. That was given to me. Now a sub n, let's say we're looking for the second term. Well, I would do 3 times a sub n minus 1. Now my n was 2. So 2 minus 1 is 1. Well, that means a sub 1, that's the previous term. This means previous term. And so this is going to give me 17. Now for the next term, my formula says you do 3 times the previous term and then add 2. So 3 times 17 is 51, then we've got 53. Okay, and then we keep going. Plugging these into my calculator. Excuse me. We have 161. So the first 4 terms of the sequence are 5, 17, 53, and 161. Okay. I always put the dot, dot, dot because this could go on forever. One of the things about a recursive formula is in order to find any term, you need to know the previous term. For example, here, I wasn't able to find the 4th term if I didn't have the 3rd term. Okay, so you'll notice that these are always going to match. Okay, the previous term for over here, and then also over here. So it always connects back to the previous term. Okay. All right, so take a few minutes, go ahead and pause the video and try these next 2 problems. All right, go ahead and check your solutions for examples 3 and 4. All right, so moving on to factorial notation. So if n is a positive integer, the notation n factorial is the product of all positive integers from n down through 1. So what that means is, and it's easier to see this when we look at the bigger numbers, 4 factorial is 4 times 3 times 2 times 1. You're just multiplying, starting with this number all the way down to 1. Okay, so if I multiply these out, I end up with 24. Okay, 3 factorial would be 3 times 2 times 1, which is 6. 2 factorial is just 2, and 1 is just 1. Okay, so sometimes you see factorial notation when we're talking about sequences. Okay, so with that said, finding terms of a sequence involving factorials. So if I were to find the first 4 terms, that would mean I've got a sub 1, okay, would be 2 to the first on top, 1 minus 1 factorial on the bottom, okay? So in my numerator, that's just 2. On the bottom, I have 0 factorial, okay? Now on the previous page, we saw that 0 factorial is equal to just 1, so I'm gonna put that up top. Okay, so that means I've got 2 over 1, which is just 2. Okay, now if I'm looking for the second term, 2 squared on top, 2 minus 1 factorial, means we have 4 on top. This simplifies to 1 factorial, which is just 1. And so I end up with 4. Now we get into the third term. So 2 to the third power. 3 minus 1 factorial. So I have 8 on top, 2 factorial on the bottom. So that's 2 times 1. So this simplifies to 4. And finally, we've got 2 to the 4th power on top. 4 minus 1 factorial. So that's 16 on top. This is 3 factorial, which is 3 times 2 times 1. So I end up with 8 over 6, which is 4/3 if we reduce. So the first 4 terms of our sequence are, we'll list them over here, 2, 4, 4, and 4/3. Okay. Now, if I'm just asked to evaluate, this word means find the value. Okay, we don't need to find a sequence or anything like that. And let's think about what's going to happen here. So if I've got 10 factorial, that means it's all these numbers multiplied. Over 2 factorial, so that's 2 times 1, times 8 factorial. Now what ends up happening is that you've got the same thing on top and bottom for all of these terms. Okay, so you'll notice that you're left with 90 divided by 2, which is just 45. Okay, so a lot of times you're going to see things cancel out. Now, when we have something that looks like this has variables in it. What would happen if I were to put a number in? Let's say I put 5 in. 5 plus 1 factorial over 5 factorial. That means we're starting with 6. 6, 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. So what ends up happening is we're left with 6. Now you'll notice the n value I started with was 5, but I ended up with 6. That was 1 more. That means n plus 1 is how this simplifies. Okay, and you can try another example to see if it works. Let's say if I put 9 plus 1 factorial and 9 factorial. That means we're going to have 10, 9, 8, 7, 6, 5, etc. And then 9, 8, 7, dot, dot, dot. So all of this is going to cancel, leaving me with just 10. So it's always, in this case, 1 bigger than the number that I started with. That's why I called it n plus 1. Okay. All right, so our last section is summation notation. So summation notation is just a different type of notation that shows you're adding up a bunch of numbers. And we use this symbol over here called sigma. Sometimes you guys will see this called sigma notation. Okay, so the sigma is going to have 2 numbers usually. The bottom number is often your variable, and it's saying the number that you're starting with, okay? So index of summation means your starting term number. So if I'm starting with 1, that means I'm starting with the first term. N is the upper limit of summation, which is your ending term number. Okay, actually the 1 I suppose I should put let's see. So the starting term number is the 1. Okay, the I is just your variable, which is your index of summation. So this is easier to do when you look at an actual example. So notice I've got a sigma starting at 1 and ending at 4. That means I'm starting with the first term, ending with the fourth term, okay? So let's say I had A1, A2, A3, and A4, okay? I'm gonna plug 1 in for I. So I was the variable. I'm gonna plug it in, plug 2 in, plug 3 in, plug 4 in. Okay. Now, summation notation tells me that I have to take all of these values, so I have 2, 5, 10, and 17, and add them up. Okay, so when I add up all these numbers, I get 34. So the value of the sigma is 34. So over here, we're going to start with the second term, and you don't even have to write out the notation here. So we've got negative 2 squared minus 5, negative 2 cubed minus 5, negative 2 to the fourth minus 5, negative 2 to the fifth minus 5. Now I'm stopping at the fifth value that I plugged in because I started with 2 and I'm ending with 5. Okay. So these are going to give me negative 1. Okay, use a calculator if you need to. This is negative 8 minus 5. Okay, and so now we want to add all these numbers together. Negative 40. Okay. Now, this last one's a little bit different because you'll notice there is no variable. So let's say I have a sub 0, a sub 1, and a sub 2. I've got 0 as my starting term number, 2 is my ending term number, and I've got all of them in between. Now, I have nothing to plug in. So my first term is just 3. The next one is 3. And the last one is 3, because there's no variable, nothing to plug in. So if I add those all up, I end up with 9. Okay. All right, so now what if we're given the sequence, but we want to write it into summation notation? So I'm going to start by drawing the sigma symbol. And we're starting with, we can call it whatever variable we want. Let's call it I. I equals. Now, if you want to check to see what the pattern looks like, notice I'm starting with a base of 1, I'm ending with a base of 7. So I can say I'm going to start with 1, and I'm going to end with 7. And you want to check to see, well, what does this sequence look like? Well, that number, whatever was over here, is the base. I'm going to call it I. And notice it's always raised to the third power. So if I were to write this out, I would have 1 cubed plus 2 cubed plus 3 cubed all the way up until 7 cubed, which is exactly what we have here. Okay. Now if you look at our next sequence, we want to see, okay, what patterns are we noticing? Well, if you look at the denominator, notice this is 3 to the first. This is 3 squared. That's 3 cubed. And this last one is 3 to the n minus 1. Well, what does that mean exactly? Well, notice that this, I'll use pencil, this is my first term. That's my second term, third term, fourth term, nth term. Okay? So with my second term, notice I raised to the first power. With the third term, I raised to the second power. Fourth term, I raised to the third power. It was always 1 less. So with the nth term, it's to the n minus 1 power. So if I'm looking at our sigma notation, really what I'm starting with is, And actually our formula, you've always got 1 over 3 to the n minus 1. Lucky for us, the formula was given already, even though we probably could have figured it out. And we're starting with 1. So let's call this n, because that's our variable. And we're ending with n, that's our last term. I started with the first term, I'm ending with the last term. Okay, so you're not always going to have numbers. Sometimes you'll have variables in there too. All right, guys, homework is posted. It will be due tomorrow night by midnight, so please get that in on time. We do have a quiz this Friday. It covers the last section of Chapter 9 and this section. I know they're unrelated, but the problems will just be separate, and they will only relate to those 2 sections, okay? All right, feel free to call in during office hours if you have questions.